This unit continues our journey through the world of nucleophilic substitution reactions. Here we're going to focus on the so-called Sn1 reaction mechanism. In the last unit, unit number 42, we were talking about Sn2 reaction mechanisms. Here we're going to compare and contrast that with Sn1 reactions by going through the mechanism that an Sn1 reaction progresses through, and we are also going to talk about features of the Sn1 reaction mechanism. As a reminder, when we're talking about nucleophilic substitution reactions in general, what we are referring to are reactions where we start off with a nucleophile, that is an electron-rich species that has electrons available to donate. So we could think of this as being a Lewis base, because Lewis bases are electron donors, also known as a nucleophile. And that electron-rich species, or the so-called nucleophile, is really drawn to electron-poor atoms, specifically electron-poor atoms that have a leaving group bonded to them. So in this case, the carbon atom will act as our electrophilic atom. And that carbon atom is electrophilic, meaning electron deficient, because it's bonded to an electronegative leaving group, an atom or group that is able to break away from the molecule during the course of the reaction and be replaced with the nucleophile. So in the end game of the reaction, what's happened is that the nucleophile has come in and replaced the leaving group. So the Sn2 reaction mechanism is one of the mechanisms we talked about for this reaction in the last segment. In this segment, our focus is on the so-called Sn1 mechanism. So let's go ahead and dive into that. So for the Sn1 mechanism, we're going to list some key features and observations that we can make about reactions that proceed through the so-called Sn1 mechanism. Remember, when we talk about the term mechanism, what we're referring to are the steps required to go from the reactant to the product by using electrons to make and break the chemical bonding that is going on during the course of this process. So we're trying to explain this process, and to explain the process of an Sn1 reaction mechanism, we can make a few observations. First off, much like we did with the Sn2 reaction, we can look at the rate of the reaction and how that relates to the concentration of the nucleophile and the concentration of the electrophile. So in the case of the Sn1 reaction mechanism, just like all mechanisms, we'd have a rate constant K, which we'll fill in generically there as K. And then if we measured the response of the total overall reaction rate to changing the concentration of the nucleophile and the electrophile, what we would find is that the reaction rate depends only on the concentration of the electrophile. We could change the concentration of the nucleophile up and down all day. That's not going to impact the overall rate of the reaction. So since the rate of the reaction depends only on the concentration of the electrophile, we're going to put in the rate as K, and then in brackets for concentration RLV. We remember that RLV is referring to the carbon atom that has a leaving group bonded to it. In other words, that's the electrophile. So the rate of this reaction does not depend upon the concentration of the nucleophile. So rate not dependent upon the nucleophile concentration, since the nucleophile doesn't appear in the rate equation. Based on this observation, what we can conclude is that the rate limiting step of this mechanism, the rate determining step, in other words, the RDS, does not involve the nucleophile directly. In other words, the nucleophile does not participate at the slowest step of the mechanism. So the nucleophile doesn't participate in the slowest step of the mechanism, where the slowest step of the mechanism is the one that has the highest activation energy, the highest energy barrier preventing that step. So rate determining step does not involve the nucleophile. In other words, the nucleophile doesn't participate in the slowest step of the reaction mechanism. Because when we look at each step of the reaction mechanism, we can look at the energy required for that step, specifically the activation energy required for that step. And what we're going to find is that the slowest step of the Sn1 reaction mechanism doesn't involve the nucleophile being present at that step. All right, so another thing that we can say about the fact that our rate depends only on the concentration of the electrophile, that is the molecule has the leaving group bonded to, or RLV up there, is that we can describe the reaction as being unimolecular. So we can describe the rate determining step specifically as unimolecular, meaning that it only involves one molecule, that is the electrophile, rather than involving the interaction of the electrophile and nucleophile. So unimolecular, meaning one molecule, is going to determine the rate of the reaction because there's only one molecule involved at the slowest step of the mechanism. And this is the origin of why this is called an Sn1 reaction mechanism. So Sn stands for substitution nucleophilic, and the 1 there is referring to the fact that the rate determining step is unimolecular. So that's how we can remember the difference between Sn1 and Sn2 in the terminology is that the 1 there indicates that the rate determining step is unimolecular. It involves only one molecule, that is the electrophile. On the other hand, the Sn2 reaction mechanism had a bimolecular rate determining step. The slowest step of that Sn2 mechanism was where the nucleophile and the electrophile came together, and so the rate was determined by the concentration of both of those species, whereas here the rate depends only on the concentration of the molecule that has the leaving group bonded to it. So that's going to be our rate equation that we can observe for an Sn1 reaction. And we could definitely measure that experimentally by going into the lab and doing a bunch of nucleophilic substitution reactions where we vary the concentration of the nucleophile and the concentration of the electrophile, and we would find that the rate of the Sn1 would be impacted only by changing the concentration of the electrophile. All right, so other observations that we can make about this reaction is that if we run this reaction starting with a carbon bonded to the leaving group where that carbon is a chiral center, that the product is going to typically be a mixture of the R and S configurations at that chiral carbon. So in other words, the reaction we can generally describe as being not stereoselective. It does not have a preference for what stereochemistry is made in the product. So the Sn1 reaction mechanism, if we look at it from a stereochemistry perspective, we can describe it as being not stereoselective. So remember that the term stereoselectivity referred to a preference for making certain isomers over other certain isomers. So for example, a preference to invert the stereochemistry from R to S or S to R when we were doing an Sn2 reaction in the earlier segment. Here, since the reaction is not stereoselective, what that means is that if we start with a material that has a chiral carbon at the leaving group, then the product is going to end up being a mixture of both of the configurations at that location. So not stereoselective, and to illustrate that, if we start off with a chiral carbon bond to the leaving group, in other words, that carbon is specifically R chirality, the product at that location is going to be a mixture of R and S. There's going to be no preference for maintaining that stereochemistry of R, or no preference for flipping it to the S chirality. Instead, the product is going to be a random mixture of the R and S, typically a racemic mixture, where racemic mixtures are defined as an equal mixture of the R and the S enantiomer there. So that's going to be another observation that we could make about this reaction if we were to go through in the lab and do this and look at the stereochemistry of the products that resulted. The third observation that we can make about an Sn1 reaction is that this reaction mechanism occurs most readily at tertiary carbons, sometimes at secondary carbons, and very, very rarely at primary carbons. So when we think about this reaction, the reaction is going to occur best at tertiary carbons that are bonded to our leaving group. Sometimes it will occur at secondary carbons, and very, very rarely at primary carbons. It's only generally going to be in some very specialized cases that it occurs at primary carbons, and those specialized cases are beyond the scope of what we're going to get into in this class. So when we think about what types of carbon atoms bonded to the leaving group are going to react best here, definitely going to be best to do it at a tertiary carbon. And so our mechanism that we come up with will need to explain and justify why the SN1 reaction happens best at a tertiary carbon and worst at a primary carbon. And finally, the last observation that we'll add to this list of things that we can note about an SN1 mechanism is that with the SN1 mechanism, we will sometimes see that there will be carbon skeleton rearrangements. So we'll say that carbon skeleton rearrangements sometimes occur. So when we write out a mechanism for this, we will need to eventually justify why it is the case that we can sometimes observe rearrangements of the carbon skeletons during the course of this reaction. When we say a rearrangement of the carbon skeleton, what we're referring to is the fact that sometimes in going from reactant to product, you will be able to observe that a carbon atom has moved from one place in the molecule to another, or a hydrogen has moved from one place in the molecule to another. In other words, the skeleton of the molecule has rearranged in terms of where the atoms are outside of just the leaving group being replaced with the nucleophile. So let's go ahead and try to create a reaction mechanism that can explain some of these observations that we make about an SN1 reaction mechanism. So we'll go ahead and shrink that down, and we're going to go through the mechanism for an SN1 reaction and try to tie that back to these observations that we can make about this reaction. So let's go ahead and do a specific example of an SN1 reaction. So the specific reaction that we will take a look at here, I'll go ahead and write on the board, and then we'll work through step by step a mechanism of how to go about getting the product. So we'll go ahead and take a look here at the example problem in the upper right corner of the board, and we need to write a step-by-step process here that enables us to explain these observations that we've highlighted there in yellow. So it turns out the first step of an SN1 reaction mechanism is that the leaving group breaks away, and we have to look back at our molecule and think about what the leaving group is going to be. The leaving group is that most electronegative atom that's bonded to a carbon. So that's going to be the chlorine atom here, breaks away from the carbon, and that's going to form our first step of the mechanism. So I'll go ahead and write that out as its own step, that the leaving group breaks away. It's no surprise that this is the slowest step of the mechanism, the rate limiting step, because we're going from a starting material that has no formal charges that is relatively stable to a product of this reaction that will be a carbocation, meaning a relatively unstable intermediate. So this is definitely going to be energetically uphill. So we break the carbon-chlorine bond. That is the weakest bond in the molecule, so it is the one that is most prone to breakage there. And one of the things that does help this step occur is the fact that we make out of this step a relatively stabilized chloride anion. We know that the chloride anion is relatively stable because chlorine is among the most electronegative atoms on the periodic table. Our other intermediate is going to be our carbocation. So I'll go ahead and draw that out. Now keep in mind that once we've broken away the chlorine atom and we have a carbon with just 3 bonds to it, that carbocation carbon, that's going to be a trigonal planar carbon. So it's going to be a carbon that lays completely flat. This will have implications about the stereochemistry outcome of the reaction. So leaving group breaking away is step 1. I'm going to go ahead and label that as the rate determining step, the slowest step of the mechanism. And this fact that this is the rate limiting step allows us to account for the fact that the overall rate of the reaction is dependent only on the concentration of the carbon atom of the molecule that's bonded to the leaving group. So right there, our molecule that has the leaving group bonded to it is the only thing that participates in the slowest step of the mechanism. That's what we see here at step 1. So step 2, now that we have broken away the leaving group to make a carbocation, we have a carbocation intermediate that's relatively unstable. So that's going to be what we focus on in the next step for what's going to react. And in the next step, what's going to react is now that we formed this carbocation, the carbocation is very, very, very electrophilic because it has that positive formal charge. So nucleophiles are going to be exceptionally drawn to that carbocation. So in the second step of the mechanism, what's going to happen is that the nucleophile, which we use that dot to emphasize that it has to have a lone pair of electrons, is going to attack, and we say that something attacks, we mean that it's forming a bond to the carbocation. So let's go ahead and draw that out. I'm going to draw our carbocation intermediate that we formed as a result of our previous step in step 1. And then we'll show our nucleophile that is going to be the oxygen atom of our methanol, CH3OH, attacking that, because we have to have a lone pair of electrons or a pi bond acting as the nucleophile. When we look at our reaction mixture, when we think about who's who and what's what, it's certainly the case that that methanol has to be our nucleophile, because that's where we see our lone pair electrons available. So we'll bring over our lone pair electrons from the oxygen. So we start at the oxygen atom with our electrons. We end on the carbon atom right here. So that's where my arrowhead shows is the destination of those electrons. We're showing the formation of a bond between the oxygen and the carbon here. Let's go ahead and draw what would result from that step. So I'll go ahead and draw in green just to keep my color coding the same, and red for my bond here that I've just made. So we made a new covalent bond there by taking the lone pair of electrons from the oxygen and plugging those on over to the carbon. And then our oxygen atom is now bonded to the carbon. We still have that hydrogen that was bonded to the oxygen in place, and the CH3 group there as well. There's also still one set of lone pair electrons on that oxygen, the ones up top that haven't reacted. So we calculate the formal charge on that oxygen, and we come up with it having a formal charge of +1. All right, now onward to step 3. The third and final step of the mechanism is generally when you're working with organic molecules, the product of interest is going to have no formal charge on it. So what we need to do is find a way to get rid of that positive formal charge on our oxygen atom here. So to accomplish that, we're going to do a deprotonation step. When we say deprotonation, we're implying that this is an acid-base reaction, and we look from the perspective of the organic molecule of interest. So we're going to be deprotonating that oxygen atom of our intermediate here. So this is an acid-base reaction, removing a proton from our intermediate of interest there. Let's go ahead and draw that out. So I'm just drawing the product that resulted from the previous step. I'm going to draw that oxygen hydrogen bond in explicitly and put that in green there to emphasize it to you. And remember, we had that positive formal charge on the oxygen. We don't want to forget that. So in the deprotonation step, what's going to happen is that our organic intermediate is going to act as the acid, meaning it's going to lose a proton during this step. In other words, it's going to get deprotonated. It's going to lose that proton there in green. And it is going to lose its proton by reacting with a base, as is the gist of acid-base reactions. So we look back and we see what can act as a base. Usually the nucleophile can play double duty and also act as a base, because we're thinking here, when we think about what's happening, we're thinking about what's happening container-wide. And in the container of methanol and our alkyl halide, there are millions and millions of each of these two molecules. So certainly there's some additional methanol floating around in solution to come in, use its lone pair of electrons, acting as a base. We define it as a base because it's grabbing that proton from our so-called acid. The oxygen-hydrogen bond breaks, and the electrons from that bond go on to the oxygen. Now we'll go ahead and draw our reaction arrow here, and that will take us to our final product of this reaction. So we go ahead and draw out our carbon chain here, trying to keep everything in order. And now that we removed that green hydrogen, now we're left with just an OCH3 here. Two sets of lone pair electrons on this oxygen, because we already had one to start with right over here, and we picked up a second set of lone pair electrons by breaking that oxygen-hydrogen bond and taking those blue electrons from the blue electron pushing arrow, bringing those over onto the oxygen. So there we go. Our other product of this reaction would be the CH3OH2, because our methanol there picked up an extra proton, so now it's CH3OH2, and there's a positive formal charge on that oxygen. So that takes us to our product here. Now let's take a look, based on the mechanism that we've drawn, at how we can explain these different observations. We mentioned previously that the Sn1 mechanism we can measure as having a rate that's proportional to only the electrophile, the molecule that's bonded to the leaving group. We saw that to be the case there at step 1, because step 1 we deemed to be the slowest step of the mechanism, the step that would have the highest energy barrier to get over. So if we were drawing an energy diagram, that would be the one that would have the highest activation energy. We also observed that the Sn1 reaction is not stereoselective, meaning that if you start with a chirality of R or S at a chiral center, the product is going to be a mixture of the two. So let's illustrate that for what's happening here and justify why we would observe that this reaction would not have a preference for one stereochemistry over another. So our starting structure up top, if we were to assign the stereochemistry of that, going back to our concepts of chirality, our chiral center is right here. And if we looked at the rankings of those four groups, we would see that the lowest ranked group there is actually the methyl group, number 4, 3, 2, 1. So going 1, 2, 3, and remembering that our lowest ranked group needs to point away from us, but instead it points toward us, meaning that this is going to hence be the S enantiomer. So we start with the S enantiomer here. Okay, so we start with the S chirality of this molecule, and then once the leaving group breaks away, I mentioned the fact that the intermediate there is no longer tetrahedral, but instead it's trigonal planar. Trigonal planar, planar of course implies flat, and what flat means is that the nucleophile then, when it comes in and attacks here at step 3, can come in and attack from either the top face of the molecule or the bottom face of the molecule, and that will lead to a mixture of the R and S product. So here at step 2, the nucleophile attacks from either the top or the bottom. So this is unlike the Sn2 reaction where the so-called backside attack was favored to give the inversion of stereochemistry. Instead, there's no preference for the directionality of the attack. So the nucleophile attacks from the top or from the bottom face. That's going to lead to either the R or the S product. So as we take a look at the intermediate that results from step 2 here, you'll notice that there is a chiral center that has now formed in that molecule right there where I've put the star. And therefore, that chiral center would end up being a mixture of R and S. So then we continue onward, and the third step is just deprotonation. So that lack of stereochemistry preference is going to be continuing onward here. And so when we get to our final product, in actuality, we should draw out a second structure as well to illustrate how we can make the two different enantiomers of this, the pair of enantiomers. So go ahead and draw one of the two stereochemistries, and then in order to get to the other one, all we really need to do is flip all the dashes to wedges and all the wedges to dashes. So we'll go ahead and do that right here to give us our enantiomer. So illustrating that this is not a stereoselective process, we make both of the possible stereochemistries at our chiral center. So not stereoselective due to the fact that the intermediate is trigonal planar. All right, third thing on the list we can look at is why is this reaction going to occur best at a tertiary carbon bond to the leaving group? Sometimes it'll occur okay at a secondary carbon, and rarely does an Sn1 reaction occur at a primary carbon, rarely to never. So it's best at a tertiary carbon because at our rate limiting step there, step 1 of the reaction mechanism, we make a carbocation intermediate, and tertiary carbocation intermediates are the most stable. So when we're thinking about the relative stability of this intermediate and how fast it can form, the more stable the intermediate, the more able it will be to form. And when we think about stability of the carbocation, we're going to see that a tertiary alkyl carbocation like we have here is more stable than a secondary carbocation and more stable than a primary carbocation. Why is it the case that tertiary carbocations are most stable? It's going to be explained by induction. So if we take a look here in the lower left corner at our carbocation. So if we have a tertiary carbocation like so, and we'll just compare it here to a secondary carbocation like this. Keep in mind that alkyl groups are electron donating by induction. That's a concept that comes up over and over and over again in the field of organic chemistry. So alkyl groups donate electrons by induction, by that bond polarization effect. And so alkyl groups are going to tend to stabilize carbocations because they're going to be able to send electron density over toward positive formal charges. So we have, in the case of the tertiary alkyl carbocation, we have 1, 2, 3 alkyl groups to donate electrons. Those 3 methyl groups are each electron donating. So they're all going to be trying to send electron density over toward the positive formal charge and therefore help to eliminate some of that positive formal charge. On the other hand, a secondary carbocation only has 2 electron donating alkyl groups, and so it's going to be less stabilized by induction. A primary carbocation is just going to have 1 alkyl donating group, and so it's not going to be very stabilized at all. And so the reason that SN1 reactions happen best at tertiary carbons is because tertiary carbons are going to lead to the best carbocation possible, the one that's most stabilized by induction. And then the last thing on this list here of criteria that we can evaluate for an SN1 mechanism is that carbocation rearrangements sometimes occur. What we're going to see in the next video segment is that we can, in some cases, do an additional step of the reaction mechanism to allow us to convert a relatively unstable secondary carbocation into a more stable tertiary carbocation. That's going to be a favorable thing to occur in reaction mechanisms in cases where it's possible, because it's going to take a higher energy, less stable secondary carbocation, convert it into a lower energy, more stable tertiary carbocation to continue through the pathway. So we'll focus on carbon skeleton rearrangements in the next segment. So for now, we'll conclude our basic SN1 reaction mechanism, and we will be revisiting this again in the next segment, as this is one of the really, really central reactions that we observe in organic chemistry.